Hello, everybody. My name is Pieter Blok from the University of Tokyo. And during the next 2 minutes, I'm going to present potato yield estimation on the harvester. Using high throughput 3D shape completion. It's actually going to answer your question, Aaron. So please be aware. So in the first place, why do we want to do this? So detailed information on marketable potato yield is a very important metric for farmers because then they can optimize their cultivation methods. And with the current state of the art in hardware and software, it's relatively easy to mount RGBD cameras on a conveyor above the harvester. And with that information, you can estimate the yield of the potato. But one of the challenges when having RGBD images, which can be seen, let's see, in this graph, that it's the point cloud is only partially completed. So actually you underestimate the actual volume. So by taking that problem into account, we have developed a shape completion network. And that shape completion network is using the RGBD input of the camera. It encodes it to a latent vector. And then from the latent vector, it decodes it to a complete point cloud. And I've heard a lot of people talking about high throughput, right? So they talk about minutes, they talk about seconds. We can do this in 10 milliseconds. So just to place it in perspective. This is a simulation of our method. So you see it turning, of course, but on the left you see the partial point cloud from the RGBD. And then in the middle you see the ground truth. And on the right you see our shape completion network. And going from, in this case, left to right only takes 10 milliseconds. And on the right you also see the camphor distance, so that's basically a metric for how well it represents the ground truth shape. Pull up your phone. We still have, I'm already over time, but please pull up your phone to scan the QR codes for the code, which is available on GitHub, and a preprint is available on Archive. And my poster number is 60. So Aaron, you especially, please come and we will have a detailed talk. Thank you.
Sorry, it's me again. This is Wei Guo from University of Tokyo. On behalf of Global Weight Consortium, I wanted to introduce a new version of the Global Weight dataset, which is Global Weight full semantic segmentation of complicated canopies. The biggest feature here about this work probably is the author list. You see a huge amount of the author list, and we have like more than 15 institutes join this international initiative, and that's good. I don't know how many of you have used this Global Weight dataset before, but we already have run 2 different versions of it until now. And the initial version, we have 7 countries got involved. It's only focused on the head detection, and we run the computations very successfully. We got a lot of citations from all over the world. People like this dataset. The dataset it's also became a standard dataset in Euro. So if you use Euro, you just use one code. You can call this dataset out to practice your model. And that's it. What's new? So the global weight dataset version 1 and 2 is more focused on the detecting the head from the pictures. But the new version is like this. So you have the full semantic segmentation dataset that can train your model to have the different organs from the dataset. And the features for the new version of the global weight dataset is like this. We have more class, we have more stages from emergency to the maturity, and we have a very diverse dataset over here, and the class is not real balanced. So it's a big challenge for the community, especially for the computer vision community. This is a timeline of the global, the new data set. We will release this data set soon, so please keep your eye on our data set and visit our homepage. We'll also run the competitions in the coming next year, probably 2 times. So if you want to win the competition, please check our announcement soon. Also, we have a huge amount of the unlabeled data set as well. And I also wanted to introduce you the new leader of the global data set, Andres. He's not making this trip to here, but if you have questions, ask him or ask me directly to my poster. That would be great. And at least I would like to thank for the fundings. I will say like we still have a lot of space over there. So for those industrial partners, if you wanted to fund this wonderful project, come to me. Thank you.
Good afternoon, everyone. I am Mashiro Okada, a PhD student at the University of Tokyo. Work for some of the wave control things using the UAVremote sensing data and models. This picture was taken in the soybean field. The firstly, when I saw this picture, I couldn't believe this is the actual soybean, the production field, because this is a literary bush, just bush. So obviously, the weed is the biggest obstacle in the production field. Usually, the herbicides or tillage are used for the getting rid of the weed from the field, but it is impossible to all the weed from the field. So the weed, they give the huge impact on the yield, the working hour, and the cost. The planting density is the working is a key component for the weed control, because if the soybean form the dense canopy, light is blocked by the canopy, and which is directly connected to the suppressing the weed growth. But the problem is it is not revealed which combination is best for the weed control, which means that the combination of the cultivar and the planting density. So to find the optimal combination, a further experiment was conducted in the 2023 and the 2024, and we did the 2 things. The first, we constructed some model to predict the light interception rate from the phenotype of the above ground trait via some the growth prediction model from the accumulated summer unit, and then we validated the transition of the light accumulated the parallax using the 3D canopy data, and it's a specific software named Helios. And I will tell you the more detail on my poster. Thank you for listening. My number is the 58. Thanks so much.
Hello, everyone. I'm Nick Shepard. I'm a PhD student at Texas A&M, and today I'm going to talk to you a little bit about my work in MAIZE tassel detection. So I believe that automating, scaling, and deploying image-based phenotyping is critical for modern agriculture, as traditional methods for phenotyping are often time-consuming. They can be subjective, prone to error, and labor-intensive. Automation enables a more consistent and efficient data collection at a scale unattainable with these manual methods. So in my study, we focused on MAIZE tassel detections, comparing manual field observations with 15,000 UAS drone images obtained from 30 flights in 4 different locations. The key finding was that UAS detection yielded a greater repeatability in the environments with the highest image resolution. And those environments also happened to be genetically unrelated to the ones that we trained the model on. And this was all capable without necessitating higher computational complexity. And if you look, the model that we used is compared to a few other higher complexity, faster RCNN or RCNN models. And we just used a basic Keras TensorFlow model here, which was optimized with the Optuna package. And I think, that, again, one size does not fit all with these approaches, so it's important to optimize to what you have. I believe that future automation should come in the form of image acquisition, so either satellite imagery for phenotypes that are resolvable at lower resolutions, or incorporating multispectral and hyperspectral, as I'm sure many of you are interested in doing. So the big part for this was built on a 2024 review that said for programs that either have or are interested in incorporating UAS technology, up to half of them were apprehensive to do this because of either the cost of the software as well as the devices, or a lack of experience in analyzing the data. So our model addresses both of these by balancing simplicity and accuracy, making analysis more accessible for real-world use. QR code is for the preprint. My poster is at spot 64, and thank you for your time.
Hello, I'm Eleanor, and I'm here to share a data science project I did on tree phenotyping and tell you how to train your own YOLO computer vision model in 5 easy steps. So YOLO stands for You Only Look Once, and it's a very popular category of computer vision models that it's named that because it does localization and classification in one pass, therefore being faster. And it's a nice state-of-the-art general purpose computer vision model for things like dogs and cars. And I wanted to fine-tune it to train it on aerial imagery. So for my label data, I had an extremely high-quality curated data set from Michigan State University campus tree database. It's about 20,000 trees with traits and locations and species, etc. And then I matched that to aerial imagery that just similar to Google Earth that I pulled down from Esri World Imagery. And once you have your label data and your images, I formatted everything and matched the data based on GPS location for the YOLO model to train. I'm not going to get into all that right now. Once I had the data all accumulated, formatted, divided, test, train, split, etc., it was actually, this part actually was easy to train the model. The YOLO package is, I think, pretty user-friendly for fine-tuning models. Then step 5, evaluate your model performance. Sadly, my model still needs a lot of work. As you can see from the example images, it has a hard time distinguishing trees from background, and it usually miscategorizes them as background. So I have some additional work I need to do to fine-tune and improve that model. I would love for you to come talk to me at poster 59 with the full details of this project, or talk about computer vision. I'm also shopping for a new job. And I would like to express my appreciation for my good friends and colleagues at Michigan State University, University of Michigan, and the National Science Foundation for funding me to come here. Thank you very much.